Today, we're and the question that I saw was, how do you make a relative pointer that points to itself? And the answer is it just works, which I will just show and then I'll explain. So check that out. Today, you can check that out. Today, we're going to talk about pointers and the fact that pointers are big and inconvenient sometimes. You know, we live in this world of 64-bit computers. You know, we still run 32-bit programs pretty often because our CPUs will do both the 32 and 64-bit, and our operating systems tend to do both. You know, 32-bit, especially if you're making a game, is really a problem now, right? You tend to need several gigabytes of data, and 32-bit won't let you address enough data, and so we tend to go for 64-bit. Now, the problem with 64-bit is that pointers are big. And then when I'm designing a programming language that tries to give you more convenient facilities than just raw pointers like you have in C or C++, those other things are also big, right? So in this language, there's a built-in array type and a built-in string type, and both of those actually look the same. They're like a count, right, for some number of bytes, and then a pointer to data. And on a 32-bit operating system, these would only be 8 bytes each, or in a 32-bit program. In a 64-bit program, there's 16 bytes, which starts to feel pretty large for just like a string, right? But it has to be that big because, you know, what happens if you have a string that has an unsigned 32-bit length or something, then you can only load a 4-gigabyte string, and which seems big, but is not really big given that, you know, most PCs have these days at least 4 times that much in RAM, right? So you should, if you wanted to load a 20-gigabyte file, you should just be able to like load it all into one string. And if you can't do that, then you have to start tiptoeing around what your program can and can't do, right? So for the sake of generality, if a program is going to provide some facility that standard libraries are going to use and that user programs are going to use, it has to be able to handle those situations robustly, which is why like the standard string, you know, lets you do 64 bits worth of stuff, and so does the array, right? However, game programmers like to optimize things, right? You know, if you have a struct and it's got like 5 strings in it and like 2 arrays and whatever, which is not at all uncommon, then the sizes of these things start to get really big really fast. And we'd like to crunch those down. And if the language doesn't give people a way to crunch these things down, they're going to make their own facilities for representing strings and arrays in smaller packages. And then the problem is they start to lose the convenience of having a standard way of talking about these things. If you start having to manually convert to the standard thing and back, then why do we have these native types at all, right? So one way to make things smaller is to use relative pointers instead of absolute pointers. And by relative, today we're going to talk about pointers that, rather than storing some 64-bit number like a void pointer would typically be, that could point to any virtual address that could be represented, today's pointers point relative to their own location, right? It's like instruction pointer relative addressing that's already built into the CPU, right? And this is the programming language version of that. So I'm just going to dive into some demos. If you don't understand why you would want this or what it does, hopefully this will become clear as we talk about this stuff. So first, I'm going to do something that uses regular pointers and is totally conventional and shouldn't have any surprises. And the reason I'm just doing this is to lay down establish what we're doing, and then we'll change it up as we go from example to example. So here's a procedure called nodes absolute. I'm defining a struct called node. It's got some value that's a data. It's a signed 32-bit number, and it's got a next pointer to another node, right? So this is just like you would build a linked list out of these if you wanted a linked list of numbers, right? Now, I'm going to allocate 3 nodes, A, B, and C. And instead of allocating them off the heap generally, I'm going to do a different thing today, and I'll show you what that is. I've got this thing called buffer up here, which is just an array of 1,000 unsigned 8-bit numbers, right? 1,000 characters. And this is just going to be a flat memory space that we're allocating things out of. We could very easily build, you know, a more sophisticated allocator that dynamically expands the space and all that. This doesn't do that, and it's just for the sake of simplicity today that we're doing this. So we had better not allocate anything bigger than 1,000 bytes, but we're not going to today. Anyway, so I've got this thing cursor that just starts as the whole buffer and then eats its way into that, and that's how we're controlling what we allocate. So we're just allocating things from beginning to end in this buffer linearly, right? So I'm calling allocate, and we'll look at that. Oh, it's right here. So we just, we're passing a type as a second argument, right? So we take the size of the type, we bump the cursor, here cursor gets passed as data. So we bump data forward by the size, and then we return the pointer from before we bumped it. That's all that this does. So we're allocating 3 nodes that way, bumping that cursor forward every time. We're setting 3 different numerical values, 15, 4607, and 69,105. And then I'm going to set this next pointer to make a little linked list out of this. So A's next pointer is going to be B, and B's next pointer is going to be C. And then I'm going to print out the size of the node, and then I'm going to call this print nodes procedure, which just starts at the starting node, and for every node, it's going to print, it's keeping track of some index of what node we're on, 0, 1, 2, 3, etc. It's going to print the index, and then the value field of this node, right? And then increment the index and go to the next pointer. And when node is null, it breaks out and says done. Okay? This is totally beginner linked list situation. Nothing too special. Let's run it. And we're just going to run from the compiler today for expedience. So we're not even building a separate executable. So we're running this whole program from the compiler. And here we go. So test number 1, node size is 16, right? It's 16 because a pointer, as we said, is 8 bytes. 64 bits is 8 bytes. And then this, it's 32 bits, which should be only 4 bytes, but then this needs to be aligned, right? So just like in C++ or C or most other languages, there's some padding between these 2 elements, right? So this ends up actually taking 8 bytes, 4 of which are wasted, right? And so, so our node size is 16 bytes. And then we're navigating that linked list. Node 0 has 15, node 1 has 4607, node 2 has 69105, and then we're done. So this works. That's all we're doing is demonstrating that we can build a linked list. Certainly not much exciting about that if you've programmed in just about any language, right? So we're going to do the same thing now with relative pointers. And it starts with exactly the same code with one difference. Let me show this side by side. Try to line this up in Emacs. So at the top of the screen, I'm going to put nodes absolute, and on the top of the screen on the right, I'm going to put nodes relative. So you see it's all the same. I go on and elaborate a little bit more down at the bottom, but sort of from here to the top, it's all the same on both sides, with one little difference, which is here. Here I'm saying next is not a absolute pointer to a node. It's a pointer that's a relative signed 32-bit number. So the little tilde means relative pointer in a type context, right? And this is the type of the pointer, signed 32-bit, right? Now what's going to happen then is this is stored internally as a 32-bit number. This is a 32-bit number. And then together, that's only 64 bits. So this node is 8 bytes, which is half the size of this node, right? And yet it's got a pointer in it. How is that pointer different from a regular pointer? Well, it can't point to anywhere in memory. It can only point to about 2 gigabytes plus or minus its current position. But if you're controlling your memory allocation, right, and you sort of know where things can end up and what is the range of space that things could possibly point to, then this is a very nice way to save some space. So we're doing the same thing. We're allocating 3 nodes. We're putting values in them. We're setting up the links. Here, I'm going to C's next pointer would have been null already because this field is initialized to null, especially here. Notice we didn't set it here. But here I am going to set it, and it's just to explicitly point out that even though these are relative numbers, they also have a provision for encoding null, right? If you're at some, you could be at some address higher than 4 gigabytes away from 0, which is the representation for null, and technically be unable to point at 0, but you know, we have a value reserved in the space of the relative pointers to say, oh, this pointer is null. And that value actually is 0. So if you memset your struct to 0, then all your pointers point to null, whether they're relative or absolute. Okay. Anyway, so we do the same thing. We print out the node size, and then we print the nodes. So let's go here. So now test number 2, node size is 8, and the nodes have the same values, and we're done. So that's cool. So now we're going to look a little more into how the relative pointers work. We're going to make another node D. It's going to be allocated the same way as A, B, and C. And then we're going to copy A into D. And you know, when you copy, so like I said, this pointer is just a signed 32-bit number, but you want that number to automatically change. You want it to act like a real pointer. Let me put it this way. If you start with code that's like this on the left with an absolute pointer, and then you put in a relative pointer instead, then the behavior of the code, this is arguable, but we're starting with the premise that the behavior of the code shouldn't change. You know, as long as your program is still correct, right? As long as you can point, as long as the place that you want to point is within the valid range of this pointer, right? And so if you start out with A and its next pointer points at something, and then you assign that into D, D has a different address than A. And therefore, to point at the same destination, D's pointer has to change in value from A's pointer. And so the assignment operator does this automatically, right? And so here we're just going to say D minus A is whatever the difference is in the memory locations of D and A. And then we're going to print out these 2 nodes, and it's going to show us the contents of the pointers. So D is 24 bytes later than A, which totally makes sense, right? Because it's 8 bytes per node, and A plus B plus C is 8 plus 8 plus 8, which is 24. A is a node. The value, which is this sign slot, is 15. This is no surprise. That's what we set as the first thing. And then next is this relative pointer. That's what the R means. And it says 4, meaning pointing 4 bytes later in memory from the position of the pointer, which again is no surprise because A is pointing to B. B was allocated immediately after A. And the size of this pointer, well, in this case, the size of this pointer is 4 bytes. You know, we're pointing 4 bytes later. And then this is printing the absolute address, actually, in hex. There's no letters in there, but that's a hex number. So the print statement is decoding this relative pointer for us so we can see what address it points to. Now remember, I said, then I copied A into D. And this notation is the same. This is just what C++ version of that would be, just star D equals star A, right? I'm putting the contents of A into the contents of D, right? And equals adjusts the relative pointer for us. So the value is the same. That's no surprise. The relative pointer now points 20 earlier in memory, right? It's minus 20 because B was allocated way before D. But the absolute address is the same, right? So when you dereference this pointer, you automatically get this address. And we point to the right thing. And we prove that by then we say print nodes starting at D, right? So now we're following the linked list from D to B to C, right? And so here's D, B, and C, and then we're done. So that's all great. Now the other thing to note is we didn't have to do any weird macros to decode this pointer. And it's totally type safe, right? So the compiler decodes this to a pointer to a node, right? It's exactly the same type as this once you've pulled it out of memory into a full-size pointer. So the goal of the language support is to make it transparent to be able to use these and to have all the same kinds of safety that you usually have. Because when programmers sit down, we're going to go through more examples later, when programmers sit down and do these kinds of things that we're going to show, often they'll hack them together with like just integer offsets in files and stuff. And that kind of gets messy and it's easy to make mistakes. And what we're doing is we're giving it the solidity that strong compile time type checking usually gives you. Okay. Now, we allocated all this stuff into linear memory, right? So I'm just going to save that linear memory to a file because we can. You know, normally you don't think of as a linked list as something that you can save to a file, at least without doing some complicated serialization process. But here it's all just in linear memory. As long as I'm going to load that file back on a machine with the same architecture, so the numbers are the same size and the same endianness, or as long as I know how to translate it, then this is a valid way to save the information. So I'm just going to take a new string that points at our buffer. Remember, buffer was this thing at the beginning. I'm just going to point at that, and I'm going to say, well, it's as long as however far the cursor is. And then I'm going to write that to a file and assert that that succeeded. So that's just an example that you could do that. Now, there are some limitations that you take on as soon as you do this, right? So for example, as I've said, a relative pointer can only point so far in memory, right? So if you try to copy something onto the stack, notice that D over here, when I made D, it went into that same memory buffer as everything else, right? If I try to make something on the stack, like this thing E, and I say, well, E gets the contents of A, then I'm probably going to overflow my pointer and point it somewhere nonsensical because you have no guarantee that your stack is anywhere near this thing. In fact, it is when we run in bytecode, but it's not when we run in compiled code. So this is not something that you want to do. You would get a runtime error when we detect overflow, but I don't detect overflow yet. We'll talk about that in the Q&A or maybe next time. We will detect overflow because it's important. But today we're just demoing the functionality. All right, so just as a sort of a compiler test, I implemented a super node that contains nodes just to make sure that if you have nested structs that the values get translated. But then that raised a question of like, what exactly would you like the behavior of relative pointers to be in this case, right? So I've got this thing. I'm setting the values of A, B, and C, and I'm setting A's next to C and C's next to B. So it's very analogous to what we did earlier. However, these things point internally to themselves. And it raises the question of what we want to happen. So if we make a second supernode and copy the first one, what should happen? If we follow the thesis that I said earlier about the behavior should be exactly the same as it is with pointers, then M should then be pointing into N's nodes after this copy happens. And that's what I've done for now. We'll show this in a second, but I've preserved the semantics of absolute pointers in this case. However, it might be that maybe one reason we want relative pointers is because they can be better than absolute pointers. And then we actually want equals to detect when pointers are pointing within the copied region and not alter them so that they end up pointing to a place in the new copy. That is a possibility. However, if you want those semantics right now, you can get them anyway. So you could say, mem copy, you could do that, right? Because mem copy will copy the bytes without altering them. And right now equals does alter them. Anyway, so here's what happens. So here's the addresses of these two things. N is this super node. It's got a note, hello sailor, and it's got some nodes that point at each other, right? Just like before, except this time B is last and has a value null. Should I make this wider? Yeah. Anyway, so then we made M, which is a copy, and you'll notice that the places that M points are the same absolute pointer values, right? Because I preserved the behavior of absolute pointers in this case. Not completely sure that's the right thing to do. It's interesting. All right, so let's go back to main and see what is next. Read from file. So remember, back here, I wrote this data out to a file, and just that was all that we said about that. Well, we can come back and read that data again, and I just want to show how easy it is to use this data when it's been written out in this way, which is, again, is part of the power and utility of having relative pointers like this, right? So before, our declaration of node was in a local procedure, so it's not in our scope, so I'm just putting it here again. But it's the same declaration where our next pointer is a pointer to a node, but it's a signed 32-bit pointer, right? So I'm going to load the file into a string. That's what read the entire file does. It just gets the size of the file, allocates a string that big, and like f reads the file in, right? We print out how big the file is, and then to print the contents, I'm going to cast the file data to a pointer to one of these nodes, and then I'm going to call print nodes again, right? So we're loading structured data full of pointers from a file and doing no processing, right? We're not like looking up pointers and stuff, right? So here we go. File data is 32 bytes, contents 15, 46, 07, 69, 105, done, right? So, you know, this is in a game engine or any other modern multimedia application that is asset heavy, where you want to load assets that have pointers and arrays and strings and other stuff in them, like, for example, you know, 3D meshes or entities or something like that. Then the kind of loading that you want to do is this kind of loading, where you just pull in the data, or maybe the data is already there because it's part of a bigger package and you're just pointing at a place in the data, and you don't want to have to do processing to it. You don't want to have to like unpack things into arrays and allocate a bunch of stuff on the heap and load other chunks from other files, right? And you don't want them in like a JSON or XML or other such relatively lame file format because that stuff is slow and it treats your memory badly, right? What you want to do, what all good game engines do, is they load memory in a chunk and point at it, right? And so what this relative pointer support does is it lets you do that without losing first-class programming language support for what you're doing, right? You don't have to do a bunch of hacky macros and weird things. All right, what's next? Someone is saying it's an offset relative to this. It is not an offset relative to the this pointer. There's no such thing in this language. It's an offset relative to the pointer itself and not the start of the struct. I won't go through an example illustrating that because it's not that important, but the pointer doesn't know where the start of the struct is, and there may be no such thing. Okay, let's talk about arrays. Wait, was that the right? Yeah. Okay, so I mentioned before that arrays, full-sized arrays in the language look like this. They're just a packaging of a length and a data pointer, and you might say, well, why do you do that? Well, it's good for a lot of reasons. You know, in C or C++, well, in C, if C++ people tend to get the modern C++ disease and do all sorts of crazy things, but in C and in C++ game style, you end up passing two arguments around all the time when you want to talk about an array, and the debugger doesn't know these things are associated, and etc. When these things are put together, the compiler can range check them and do all sorts of good stuff for you, right? So, you know, it's very convenient to have these packaged together, but like I said, if they're too big all the time, people may not want to use them. So here's an example of using arrays with the same relative facility, and instead of instantiating stuff by allocating in the data segment, I'm just going to do it on the stack this time. So I'm going to have 3 integers in an array, fixed size array here. I'm putting the numbers 3, 4, 5 in there, right? Simple. And then I've got a, you know, an array of unknown size. I don't know what to call this. Like, I think Go calls this a slice. It's just this count and data pointing at this, right? So the count gets 3, and the data gets the pointer to the base of this array. I don't like the word slice because it sounds very active. It sounds like you're acting on the data to cut it up, but that's not what's happening. You're just taking a view of that data. Anyway, so we're just going to iterate over there and print y whatever and then each number, right? And so here we get y3, y4, y5. Now we're going to do the same thing with x, but x is an array with 32-bit pointer, right? And we're going to assign that to source as well, and we're going to for x and print, and look, that works. And then I'm going to say z is an array of int again, and I'm going to assign that to x instead of source. And that's just demonstrating that, look, I can implicitly convert from this array to one of these and back out to a big array anytime I want, right? I didn't have to cast or do any weird macros or anything here, right? So for z, print blah. And z works, right? And so size of y, which was the big array, is 16, and size of x is 8. Now it's 8 because in addition to making the pointer small, we also make the count small, which is not a priori necessary. You can imagine some kind of syntax where you use this tilde to specify two sizes or something, but right now it doesn't really seem to be worth the complexity of doing that. So right now I just have the size, the count and the data are always numbers of the same size. And we'll see if we have real world use cases that need more versatility than that. We'll look at that later. There is more versatility that we will probably add to arrays, but it'll probably be about not having a count, like saying this array is the same length as this other array or something. Yeah. So now we're going to switch to a different example, and I'm going to do it again. I'm going to go really quickly through doing this thing with absolute arrays again, and then we're going to go relative. So this is going to be a thing called a holder. It's just, you know, a key value store where I've got some array of names and an array of values that's parallel. So we've got the same number of items in both, and the names correspond to the values, right? And I'm just going to, with absolute arrays, I'm just going to do messy heap stuff. So I'm going to say it's a new array of string, new array of float. I'm going to set names, right, to these three strings. I'm going to set the values to some relatively arbitrary numbers. I'm going to make a new, so new is just like C++ where it calls, you know, our equivalent of malloc. It's not as messed up as C++ is new. And I don't know if this is, well, let's not go on that tangent. Anyway, so I'm setting the names and the values, and I'm calling print holder. And print holder just does this, where we say what the size of the struct is and say its name, right? This is polymorphic, note, so that'll be important. Then for everything in the names array, we get the value at the same index as whatever that name is, and we print out the name, a new line, and then some spaces in the value, right? So when we print this first holder, we get size of holder is 32, right? Because there's two arrays, and each array is 16 bytes. And it says Cosimo, Violo, Ottimo, Massimo. That 16 bytes, by the way, is not the contents of the array. It's the data and count that points at the contents of the array. So it's a little bit, it's the size of the storage of the array view or array slice or whatever you want to call it. Okay, so that's just the regular old absolute part. So the relative version is much like what we did with pointers, right? So I've got this names array. It's an array with signed 32-bit elements, and values is an array with signed 32-bit, not elements of the array, but data and count on the array, right? And then we're doing all the same stuff. And let's not, this is literally the same code. So we'll just look at that and show that that works, except that the size of this, this is called holder 32 now. And the size of holder 32 is 16 bytes. Boom. Same stuff. Now, again, just like those arrays, the packed... Oh, I got ahead of myself and talked about relative... Oh, this is wrong. I'm not using relative strings yet. Relative strings is going to be the next topic. So let's skip this. Anyway, that's just showing that just like relative pointers, we have relative arrays that work the same way. Now, we can take that a step further. So instead of deciding a priori what our packing is going to be. Maybe we want to be more versatile than that, right? So I'm going to make this thing called holder sized, which is some struct. It's got arrays of names and values, but it's got a parameter, which is like some type that I'm going to pass it. And the arrays, and actually this string here too, we'll talk about size strings in a minute, as I said, but you know, the arrays are all going to be sized and relative based on this pointer, right? So I'm going to make a holder sized of 16, and I'm just going to print the size, and I'm going to make a holder sized of 8, called another holder, and print that size. And they should get smaller, right? So size of holder is 8, size of another holder is 4. So we're just instantiating these structs at these two different sizes. All right. Now we're talking about relative strings, as promised. So just like arrays, a string is a bundling of two things, a count and a data. And again, it's because, you know, zero terminating your strings, as is the C convention, is not necessarily a very good idea for a lot of reasons. It's very convenient to know how long your string is much of the time for both security and speed purposes. However, that takes space. And we already said pointers are big, and then when you double the size of a pointer, that gets kind of big, and sometimes you don't want them to be that big. So again, we're just applying the same technique. Here we're doing it on the stack, so we're copying a string into this buffer on the stack. B is some string with 16-bit count and data this time. And I'm setting the data to where this buffer is, and the count, right? And that's it. So then I'm just saying, okay, here's the size of a full-size string, and then a size of the tiny string, right? So size of A, full-size string, is 16 bytes. Size of the tiny string is 4 bytes. And then I'm printing B just to prove that it works. And B is hello. All right. Now the reason I had to do this little bit of funny thing with copying this into a buffer on the stack is because B is on the stack right now, and he can't point that far, right? Especially because he's only 16 bits per member. However, you wouldn't really, you wouldn't use a 16-bit pointer string on the stack in reality. You'd use it in a struct somewhere. So, you know, doing it on a stack is a little bit funny. I don't know why I did it that way, I just did. I got tired of defining structs. Okay, so now we're coming to the fun part. So I started out showing this holder thing. Actually, no, I didn't start that way. I started with the linked list node, but you know, with any data structure like this that has pointers to arbitrary data, like I said, when you want to do the game engine thing, you want to load it fast. You want to have it packed into memory, and you want to load it. However, you also sometimes want to operate on it. So like, if I'm, you know, if I want to render a 3D mesh in a game engine, then during runtime, when the player is playing the game, I probably just want to load the mesh really fast and not look at the memory at all, except for, you know, I don't want to process it. I mean, I just want to like load it and use it, right? But there might be other parts of my code that want to process that mesh, like maybe, you know, recompute the vertex normals based on something, or add a second set of UVs to it, or there's all sorts of things you might want to do. And you don't tend to do those things during gameplay time if you don't have to, right? And so you end up wanting to manipulate two versions of the mesh, one that's not packed together and one that is. And so I've showed all this stuff so far of like, oh, you can pack this thing and save it to a file, and isn't that neat? But, you know, you might be thinking, oh, isn't it just annoying work to have to pack something that way? You know, isn't that tweaky? Like, yeah, it's great that the language is providing type checking and stuff, but I still have to do all this tweaky packing. And actually, no, you don't have to. So I wrote a little demo of automated packing of something into a linear buffer with relative pointers. So we're going to start by calling holder with absolute arrays, right? So this is just exactly the same thing that we did at the start. It's just calling this procedure that constructs this holder on the heap and prints it out. So here we are again. This is just the same thing, nothing new here. Now, I'm just going to tell you what this does, and then we're going to go back and look through this procedure pack. But this procedure pack takes the elements of this struct and packs them into a holder struct that is sized by the second size. And that's all contiguous in memory and relative pointers, right? So at the end of this, we're going to have, you know, these arrays, and then all the contents of all the arrays flattened contiguously in memory that we could save out to a file or do whatever we want. And the first thing we're going to do is just say how much memory it is and print out the memory, right? And then we'll print out the data to prove that it's actually data structure. So we're treating it both as a linear data structure we're treating it both as linear memory and as structured data. And that's a very powerful, to have both of those views on data at the same time is very powerful. And the first thing I'm going to do is convert it to 64-bit relative pointers. Why am I doing that? Well, they're not any smaller, but it does give you that serializability that you get with the smaller relative pointers, and they could point anywhere in memory, which is very convenient. And just as a diagnostic, this will tell us how much memory our data structure is using, which is a useful thing to know. Not counting, you know, heap fragmentation and all sorts of other waste like that. Anyway, so we're making a result 64 that's packing this thing with S64 pointers. And here it is. It's 117 bytes. Here's all the bytes. You'll note that a lot of those bytes are 0 because relative pointers, when they're 64 bits, if they're pointing to anything nearby, which most of these are, compress really well because they're mostly zeros. So, you know, this thing, these are all the pointers, right? And then eventually we get to the string data, and these are mostly ASCII characters representing those names. And then there's some floating point numbers in there as well, right? So that's 117 bytes, which is what this original thing was using. So that's good to know. Most people have no idea how much their data is, right? So then we're just going to do the same thing. I'm going to say, okay, now let me pack that thing with 32-bit pointers, relative pointers again, right? And let's print that out. So we do that with 32-bit pointers down here, and it's 77 bytes. Look, it's fewer numbers because we're packing fewer zeros. All the numbers at the end are the same, right? It's just, we have way fewer zeros here. And then we'll do it again. It's like, hey, let's do it as 16-bit pointers. Oh, that's 57 bytes long, right? And then let's do it with 8-bit pointers. That's crazy. But this is a small enough data structure that everything is within 127 bytes forward and back. In fact, it's within 47 bytes forward and back because that's how big it is, right? So that's a substantial size change. We got something from 117 bytes down to 47 bytes just by ensmalling the pointers. And after each one of these, we're calling print holder. Remember, print holder was polymorphic, right? Print holder takes anything of type T, and then, you know, this is like a C++ template where as long as we can do the things that we try to do down here with it, it'll work. So we're actually passing 4 different data types, right? A holder size of 64, a holder size of 32, and so on. And we're printing this, and it works all 4 times, which is just proving that this packing down of the data that we are doing is correct and maintains all the original data, right? Now, like I said, though, they're not just one-way serialized buffers. They're also structured data, and we can treat them in both ways, and that is very powerful, right? So here's what we're going to do. We're going to take this result 8, which is the smallest one, and we're going to do some structured data. Well, first we're going to copy it. We're going to copy result 8 to a new string called copy, and then we're going to cast that data to a holder-sized S8, right? So we've got a new S8 holder-sized. And then I'm going to do some stuff. I'm going to swap the first 2 names. So I'm indexing this names array, 0 and 1, and let's swap those. And then let's iterate over all the names, and we're going to turn them all to uppercase. And then this is a little wrinkle. This full-size string here is not important to talk about right now because it'll be fixed, I think, in the final language. But there's a slight wrinkle where I have to insert a helper function here. So it's not completely transparent that I'm using relative pointer strings, but it will be. If someone wants to remind me to talk about this in Q&A so we don't sidetrack now. We can do that. But anyway, so we're going to uppercase all those names in place. And then we're going to set the values to new floating point numbers and do some math on them. And then we're going to print the holder, right? This new one that we just modified, right? So H points to copy. So we're going to print that. And look, they're all uppercase. And they've got the different numbers. So that's great. But let's prove that that was an independent copy and the original was untouched. So we print holder of the independent result 8, which still is sticking around. And that's here. The original copy of holder 8 is untouched. So we just essentially, with a mem copy, so I called copy string here. Let me show you what copy string does. Where is it? So copy string, when we copied result 8 into copy, that's just this. We say, okay, we make a string, right? Set the count to be equal, allocate the data on the heap, and then copy, right? So this is just a mem copy is all that's happening. So we're mem copying this thing, but we're getting a data structure back that we can treat as a data structure. That's great. And then as the last thing for this procedure, we're going to do something really fun. We're going to take copy, which is this version that we just futzed with and made all uppercase and stuff, and we're going to print out the bytes, kind of like we were doing here. We're going to print it out more like code, where there's a declaration and some commas between all the bytes. So it's going to look like this. And this code right here is just building that string, and we print it out. And that's exactly what we're looking at here, right? The code string to add is this. So now we're going to compile this into a totally separate program. We're going to make a new workspace in the compiler. We're going to set the build options to make an executable called separate program. Because remember, this whole thing was running in the compiler the whole time. We're going to add a file called demo relative pointer separate program. Whoops. Let me go to it. And then we're going to add this data payload string that we just printed out as well. And this separate program, all it is it's going to have some of the same stuff we had. We had this holder sized, right, which we can instantiate at any size. We've got print holder, which is exactly the same. And then we've got main. This is the whole program apart from importing the print function, right? So we've got none of the other stuff we were doing. None of this constructing the value or anything. We're just including the value in the global data, right? So we print welcome to the totally separate program. We point holder at this data payload, which is just bytes, right? And then we print it by iterating over the names and values and doing all this structured data stuff. And so I can run that. I can run tests, demo, relative, pointers, separate, program.exe. Did I get that right? Demo, relative. Oh, wait, it's just called separate program. I gave it a shorter name. I was all confused there for a second. Did I typo that? No. So it says, welcome to the totally separate program, and it prints out that data that we futzed with and messed with, right? So it's data we just exported to a separate program, data containing pointers, right? And so that's what's nice about relative pointers. And we didn't have to do anything crazy, right? We just had to say, these pointers are relative. So that's great. Okay, last thing. So I think this is the last thing, yeah. So the last thing is just to make a point that instead of instantiating things always with a signed number, like S16 or S64 to make something a relative pointer, if you put void there, that'll make it an absolute pointer just like it always was. Why would you want to go through all this and then put void? Well, maybe, for example, in the game engine case, like I was talking about, you want to make a triangle mesh that the one that you operate on has absolute pointers because you're just going to be messy with the heap and whatever, right? And then when it's time to pack it down for gameplay, you instantiate a version of that with relative pointers, whether they're 64-bit or smaller, you know, who really cares, that you can then just serialize with memcopy or saving to disk or whatever, right? So here's just an example of that. I have this node general that can have any type of pointer. This is the same as the linked list node at the start of this talk. And here I'm just going to set the next pointer to itself just to do that. So I've got a node 16, node 64. and node full, right? So node 64 is the same size as node full, but these are relative pointers and these are absolute pointers. And I'm just printing these, right? So going back to the original program. So here A, right, has a pointer pointing to itself. B has a pointer pointing to itself. C has a pointer pointing to an absolute address, not a relative address. Now, the next project, which I didn't do for today, but I hope to demo this in the future, is that I'm actually going to use this on a large data structure, like the triangle mesh in the game engine, because everything that we've done should map to that straightforwardly. There were a few other things I wanted to do on my compiler to-do list before I did that, so I haven't done it yet. Now, I mentioned that we should look at what this Pac function is. So remember, remember when we made these holders of different size? I said Pac makes a holder of a particular type. And so I'm just going to show you. Well, it makes actually not a holder of a particular type. It makes any packed version of any particular type. And here's what it does. So I'm going to leave this usage code on the left so you can remind yourself how it was used. So on the right, okay, it takes a pointer to some type, right? And then the pack type, $, is our very verbose way of saying we need to know what this is at compile time. We demoed that in a previous talk a long time ago. So the pack type, I'm probably going to change it to actually a single $sign so it looks like that eventually. But anyway, so we tell us what the type of the pointers should be, right? And what we do is we just get the type info, which tells us what all the members of the struct are, and we iterate over that. I'm just going to go through this really loosely because it's not that. This isn't a fully robust implementation yet. It's a demo implementation that doesn't handle all cases. But basically, we look at all the members of the struct, and if there's an array member, then we know that's got pointers in it. So let's note later that we need to write out the pointers. We need to write out the contents of this array and then backpatch the pointer to point to the contents, right? This is totally, if you ever serialize stuff, this is totally typical, right? So we say, oh, we've got a thing to pack. Here's where it is. Here's the source address of, where the pointer is pointing to, right? Or here's the address of the source pointer, right? And here's the destination address in the bit stream that we're serializing, right? And we just make a note of that. And then we put down zeros for now. So we just say for now, oh, the count on this array is 0 and the pointer is 0. But we're actually going to overwrite those later on, right? And if it wasn't an array, we just copy the member. And the reason why this isn't a full implementation is because it's not handling like string here or one or two other things that would be important to handle. Pointers to other structures, stuff like that. Anyway, so once we've gone through all the members and we've noted all our things to pack, now we've finished serializing the body of the main struct. We couldn't serialize that other stuff yet. You might think like, oh, well, let's recursively serialize in here, but then you break the memory of the body of the main struct, which you don't want to do. So you finish writing out the main struct, and then for everything that you said, oh, this is a pointer that we need to follow up, then you go and serialize all those contents. So I said, well, maybe it's an array of strings, in which case, we do this. Oh, actually, sorry, that's not array of strings. Maybe it's a string member. I don't actually add string members. So this is, like I said, it's an incomplete implementation, right? Or if it was an array, hey, maybe it's an array of strings, in which case, we do a special thing, otherwise blah. So all it's doing is linearly serializing and in not a particularly special way. But as I said, what that does is it automatically takes some type that whatever it is just all over the heap in memory that could be pointing to anywhere and could be very slow, and packs it into a version with relative pointers of a potentially smaller size that we can then load directly off disk. And that is everything that I wanted to say today. So I'm going to take a very short break and get a drink, and we can do questions and answers. I saw one question while I was getting ice cream and tea. And the question that I saw was, how do you make a relative pointer that points to itself? And the answer is it just works, which I will just show and then I'll explain. So first let's start with not relative pointers, right? So I'm going to say P is a void pointer, right? And I'm going to say, I'm going to assign P to the address of itself. And I'm going to say print, well, first I'll print address of P is, right? So star here is the opposite of what it means in C. It means take the address of something. It means the same thing as it does in a type. This means the address of a void, right? And this means the address of a value. So, yeah. Anyway. And then I'm going to say P is whatever, right? And that's it. So let's compile that. So star P is whatever and P is whatever. So that's absolute pointers, right? Let's make it a pointer to a relative 16-bit, right? So it should be exactly the same. Oh. What happened? Oh, sorry, S16. I do that a lot. Okay, so you'll see the same thing happens. Boom, boom. Now, why is that? Well, let me do one more thing. I'll say print the bytes stored in P are, right? And then I've got this function print bytes in the standard library that takes a pointer and then how many bytes you want to print, right? So I'm going to print bytes P size of type of P, right? So now for the absolute pointer case, this is going to not be a surprise. So right, P is this thing in memory, and the bytes stored in P are, it's a little endian machine, so they're in reverse order, but F0, B2, C4, right, 0, 4. Same thing. When it's a relative pointer, it is not actually storing the offset directly. It's storing an encoding of the offset that allows you to represent 0, but not as the number 0, right? So it actually sets the high bit. So it's a 2-byte pointer with the high bit set and then zeros in the low bits, right? So basically, the encoding that we use currently for relative pointers is if the value is 0, then the decoded value is null or 0, right? Otherwise, we XOR by the high bit, right? Which allows us to represent everything in the wide range from positive to negative, except the integer with the high bit set and no other bit set, right? Which is the negative extreme most number. Now, this may not be the best encoding. It's just the one that I picked at first. And it may be slower to decompress than some other encoding. So this one is about 7 extra instructions. They're fast instructions. You might think like, oh, 7 instructions sounds like a lot, but it's way, way, way less than taking a cache miss, bucko. So there's that. But also, well, I don't know. It's not that important. Anyway, so Fabian suggested one that is probably about 4 extra instructions. And all of these are cheap instructions, by the way. Like, we're not talking about cosine or anything. We're talking about like add or XOR or whatever. So we may switch to that one later. The disadvantage of Fabian's is you can't, his is basically add 1 instead of XOR or subtract 1, something like that. So you can't actually point at the byte 1 byte after yourself, which would not enable us to do 8-byte pointers, or sorry, 8-bit pointers, right? 1-byte pointers. But 1 byte pointers may be so small that in practice you don't really want to use them, or if you do use them, maybe you're just aware that you can't point to 1 byte in the future, and that's fine. And we can, as part of the overflow checking, which we don't have yet, we can always just detect that situation if you ever do it. So that's the current situation there. Does that make sense? Okay, let me look for instructions or questions. Relative pointer to relative pointer just works. Yeah, I mean, a relative pointer is just a number in memory, so you can take a pointer to that just fine. I mean, this is a relative pointer to anything, right? Check your second print. I don't think it's right. Oh, sorry. Yeah. Good point. I should have noticed that. Okay. So, right, this is just saying, so P is a relative pointer pointing to 0 bytes from its own offset, right, which is this address. Thanks for noting that. The result is approximately the same. It's just our print output's a little different. Someone's asking, could you give a relative pointer an unsigned number so it would only point forward in memory? Well, for now I didn't do that. I should have mentioned this in the main talk though, but relative to its own address is not the only kind of smaller pointer you might want to use. So for example, you might want a kind of a string that points into a known global string table, right? So maybe your program just has a bunch of strings and everybody in the program knows the base of that memory, and then your pointer only points into that memory. In a case like that, an unsigned value would make sense, and we may do that. It's just that I haven't added that facility to relative pointers yet of being able to specify that base. And in fact, we may, when we do that, the reason I haven't done that is because we may want to do something one step more sophisticated in general than that. So we'll see. But yeah, in that case, unsigned numbers would make sense, and you might want to do that to try to maximize how much you can reach. I simply didn't do it that way for now, just for simplicity. It was interesting enough just getting relative pointers like this working end to end through the compiler. Will the programming language provide facilities for performing endian conversion automatically? I don't think so, because I don't feel like that's super important. Maybe. I mean, maybe you could say this is a pointer at a certain endian and this is a number at a certain endian. But the problem with that is if you're going to do that somewhere in your program, I mean, you're maybe doing it everywhere. It just seems very messy. I suppose it depends on for what percentage of your data structures you use this kind of deserialization on. I don't know. I'm not convinced that it's that necessary or useful right now. You could, for example, so in the same way, okay, so in the same way that we had this pack routine that iterates over a struct and looks at all the members and does things based on the members, you could have a version of this that looks at the numbers and swaps their endianness if it needs to be swapped, right? For example. If you did it exactly like this, it would be a little bit slow because you're at runtime looking at all the members. Maybe you don't care about that. Maybe if you want it to be faster, you could make a version of this that runs at compile time and outputs code to swap the endians, and that way it's maximally fast. So I'm not convinced that there needs to be language support for it because it's sort of a post-process step that you would do after loading the data. Like, I'm not sure why you want live data to be of the opposite endian. But maybe, you know, if somebody can make a good case for why that should be that way, then I'm not necessarily opposed to it. Are there any cases where you can think of where serializing game data to human readable text is valuable? Yeah, I mean, our entity format is pretty readable. So, I mean, I've showed this before. So like every one of our entities gets saved in a format like this. This is not what that format would look like that we saw during the demo, right? This is like printing out the names of the fields and the values in human readable ways, and I can even edit the values and stuff. So when we're editing the game, I use stuff like this. But when we're shipping the game, we don't load this stuff, right? We load binary data. And the reason is because you want to start up quickly, and etc. And you don't want to fragment your memory, and there's all kinds of reasons. Oh, why did I need that full string helper function? Thank you. Okay. This is a little bit of a weird thing. So full size string. So all full size string does is it gives us a pointer to some type, which we're going to assume is a packed string with relative pointers. We don't type check it, but let's assume that. And we just say like, okay, well, actually we assert at runtime. We don't type check it at compile time. We assert that it's a string of some kind. And then we look at the type info for the string. If that type info doesn't have a relative pointer, we just say, oh, it's a regular string. Let's return it back. Otherwise, you know, we sort of decode the relative pointer ourselves. The reason we do that, even though the language itself, like I showed, the programming language itself will handle casting from packed strings to big strings, right? So why did I have to do this? Well, it's because of the following. For loops have two modes, right? When I demoed them a long time ago, they're a mode where you iterate and take the pointer to everything, or a mode where you don't put the star and you just take everything by value. And that's what we want, is we want the string by value so we could pass it to uppercase in place, because uppercase in place just takes a string, right? So we want to cast from our relative pointer string to an absolute pointer, which happens automatically, like I said. The problem is that for loops, if you do things by value like this, right now the semantics is that it makes a local copy on the stack of the value. And like I said, if you're pulling something out of global data and it's got relative pointers and you want to store it on the stack, the pointers probably can't reach anymore, right? They can't reach from the stack to global data, so then you get garbage data, right? So I can avoid that by taking by pointer. But then still, if I make a string on the stack here that I'm going to pass to this thing, I can't do it with the implicit casting right now, right? So I have to like de-relativize it myself. Now, the reason why I'm saying this is temporary and probably won't be this way in the final version is that actually, when you do this in a for loop, probably it shouldn't make an entire local copy of the value on the stack, right? Probably it should give you the value as like a read-only by reference. Basically, the equivalent of a const reference in C++, because you don't really want to copy it, right? And if you're not copying it, by the way, that sounds weird, but it's actually the same. When you pass a struct, like even a string, to a procedure, that's actually the calling convention for arguments right now, too. So it's basically saying the same calling convention for arguments you would use to visit things in the array. And then if you do that, then this problem would magically go away because the thing is still located in global data, and then the thing you have on the stack is only a full-size string, and then we're converting between those, and that works just fine. Right. The only thing you can't do is put the relative pointer on the stack. I guess I'm not sure why. Oh, right. So the other way to do it would have been this, right? But again, this says, take this thing on the right-hand side and make a by value copy of it. So it's sort of the same problem. So that's kind of funny. It's the things that, you know, this is always why you have to implement this stuff and try it out, because you never know what the issues are going to be. And that is a small issue that I hope will completely go away. Now, just because I fix it in for loops doesn't necessarily mean it might not pop up somewhere else. So we're going to see about that. But I would like it to be completely perfect and transparent, and you don't have to think about whether it's relative things that you're dealing with or not. Someone is bike shedding about semicolons. Someone's asking if this will be better for new programmers to learn game development. I think so, just because C++ is so gnarly. I mean, you could learn to program games in less serious languages like C# or, you know, Python or Lua, right? Something like that. So if you're learning, you don't necessarily have to program at as low of a level as this language is built for. But if you're learning game engine programming, then yeah, I don't know. Someone says, will there be support for memory mapped file I/O in the standard libraries? Maybe. The thing is, I mean, for a game, you don't, like if you're doing something weird like memory mapping, you probably want to control the nuances of that yourself. Like this whole, so the C standard library is built on this whole idea that like you want to fopen and then stream the file in, which is weird. Like in most cases, no, you don't want to do that. Like in games, usually I'm happier if I just have the whole file. Especially if I'm doing asset processing or something. There's in rare cases where it's like, okay, let's pull in chunks of this file. But I don't think I would use memory mapping for that. So there are cases when you would want to use memory mapping, but I don't feel like they're super standardized. So I'm not sure why the standard library would do that necessarily. I mean, it's something that people can do. They would just do it themselves. Is there support for stack allocated VLA? What's a VLA? Does that mean like virtual local address, or I don't know what that means. Have I taken inspiration from Go or Rust? You know, the topic of those languages and how this relates has been covered a number of times in different pieces in other videos, so I don't want to repeat it. Why does value pointer of a string point to void instead of a character? Actually, it points to unsigned 8. That was probably a typo when I said void. And why is a string not an alias for a char array? Because I feel like type checking in that case might be a good idea. Maybe it's not, who knows? VLA is variable length array. Okay. So the question was, stack allocated VLAs. Oh, you mean like alloc A or something? Not currently, but I have something that's probably better than that anyway that we're going to demo next time. How many are testing the compiler? It's largely just me. There's Joshua Hulsman, who's also working on it. And that's it. Very, very small team right now. We do not have GoTo currently. We probably will. I just haven't done it. Because I haven't needed to. But you probably do want it for some applications, especially when you're doing meta programming and code generation. You probably want the ability to go to. What percentage of features do I think are completed? Most of them. Like I was saying in the pre-stream, I think there's probably about 2 major features that need to get done. And then there's a slew of more minor stuff that's more like just completing what's been outlined and demoed. And then there's other small things like the GoTo thing, like implementing GoTo is probably important. I don't count that as a major feature, but it should be in. But we're kind of getting there. We're kind of converging on what the language is going to be. Someone said, what happened to owning pointers that I mentioned a few years ago? You know, that was one of those ideas where... So the first 2 talks that I gave were the initial ideas that I had about what I would want in a new language before I started doing it, right? Once I started actually implementing it, I just found through the process of making it ideas that I felt were better. So like, I don't think I very much mentioned compile time execution. I mean, I probably mentioned it in those first talks, but I didn't say the whole language was based around it or something. But I found it to be so important and amazing. You know, so things like that happen when you start doing things for real. So I sort of don't feel like owning pointers like that is a thing that I care about right now. I haven't needed it. I haven't felt a desire to do it. And so I've sort of solved some of the problems involved in that in different ways. Like, hey, if you're going to serialize out a lot of your data structures like this, or do some other things like I'm going to maybe talk about next time, then you don't need to think about deallocation as much or whatever. I don't know. Will the Pac function be part of the standard library, somebody asks. I think there will be a better version of it that can serialize either to binary or to text, I think. I think that would be a very useful thing for people to have. And then, you know, someone's going to come along and do a JSON one or something like that, but it won't be me. Someone's asking, how difficult or time-consuming will the platform-specific phase be? It depends on how you define that. Platform-specific code optimization can take as much work as you will put into it for the rest of your life. So it just depends on how we scope things and what we decide to do. Am I going to be putting any sort of limitations on GoTo? For example, maybe you can't jump into other functions or into scopes where things wouldn't be initialized. Jumping into other functions, I don't think we will support that because that is crazy. I mean, unless you mean long jump, like in C. If we do long jump, it'll be different from GoTo. Like, yeah. Into scopes where things wouldn't be initialized. I think if you use GoTo, you sign the warranty that you know what you're doing. I mean, maybe there can be a warning, especially if data flow analysis says it looks like you're using this variable and you skip the initializer. Then we probably issue a warning for that, but we won't prevent you. What's the current story for loading a closed source library written in this language? Well, we haven't written that story yet. I don't think we're going to worry about that in the very absolute initial release of the compiler, because I don't want people to wait for features like that. But my assumption is that there will be some kind of mildly precompiled representation that still allows us to do all this stuff like, you know, polymorphism and whatever on the code and name remapping and stuff like that. But that's, you know, obfuscated and with most identifiers removed and things like that. Enough that people feel relatively comfortable shipping their libraries in it and don't feel like they're going to be, you know, easily decrypted into source code. The thing is, we don't want to ruin all the language features, many of which require some representation that's early in the stages of compilation, right? So we just have to figure that out. But, you know, one of my friends who runs a software company that sells closed source libraries seems to feel like, you know, we've talked mildly about this, and he seems to feel like that would be enough for him. So. Can I briefly discuss relative pointer similarities to near and far pointers? Well, near and far pointers use like segment table and stuff, which is a weird global variable. I don't see them as the same thing. And the thing is, near and far pointers still use absolute addresses, so they don't give you this serialization power, right? And unless you, I mean, maybe somebody back in the day did some tweaky thing that let you do that, but no. I mean, you know, anything that stores an absolute address is not going to really be serializable, because your operating system is going to randomize your addresses every time you start in order to prevent people from hacking you, even though that doesn't actually help. So, yeah. Is there support to inlining assembly directly? There will be eventually. There isn't yet. Maybe that's the third major feature. How did I get the data into the separate program? Okay, so I demoed this way back if you want to go back and look. It maybe is even the first demo of this language on the YouTube channel, but basically, so here I said add the file, right? So this says, hey, this file is source code for the program. But then I just add the string. So I say add this string as though it was a file, right? And that data payload string is this string of bytes that we made. That's all that we did. It's not a particularly efficient way to add data to the program because it's being added as source code. At some point, we'll provide the ability to add just binary data directly. I've been meaning to do that for a while. Yeah. Will I still implement all the typical debug symbols that other languages provide? I think so. We want to support debuggers. I think that's important. Would I ever be interested in writing a fast Photoshop clone in this language? Not anytime soon. But I was going to write a Photoshop replacement with a friend of mine a long time ago, like 15 years ago or more. And we never got around to it. I've hinted at a language feature along the lines of compile time data transformation that's more powerful than SOA. Any more teasers on that? Not yet. I have to it's one of the things where I have to actually implement it before I start talking about it, because it might just, like I said, you have to test your thing against reality, and the more crazy it is, the more you have to test against reality. And this one is relatively crazy, and so yeah, I will talk about it when I've done it. Oh yeah, Sean is here and is talking about the Photoshop thing. Actually, I don't think I did braid for several years after that. I went off and contracted for a while. Can I give you a hint about the craziness? No, I cannot. I cannot. How long do I think it will take to make back the time I spent on the language? You know, so first of all, I'm enjoying myself working on it, so I don't think I really need to make the time back. But also, I've been really productive. Just, you know, we've got to, like, if you watch that video, which is from about a month ago that I showed at the beginning, you know, we show a dude running around on a game level there, and that's like in a fully new engine that didn't exist a year ago, in a fully new language that still doesn't technically exist, right? So things are coming along, and you know, I have other things that help, like I'm pulling over stuff from the witness and translating it, and that helps us go faster. But I feel very, very productive in this language. So I think I calculated earlier that I've really only taken a hit of like 4 to 6 months, if that. So, by which I simply mean, you know, I started this thing a year ago, and if I had started making the game straight up in C++, it would have taken at least 6 months to put together as much stuff as I have now. I feel like. Maybe that's not true, but I feel like that's true. So if it's a year later and it would have taken 6 months, then we're at minus 6 months, which is not that long, frankly. Hidden bananas. I don't know. How much of the game's editor will I provide with the compiler? All of it. So we're going to give the game engine, like, we don't want to give the entire game because then other people will sell it. But we'll give like the whole engine and enough of the gameplay code that you could push blocks around and stuff, and all the editor and stuff. Yeah. Have I tried using Direct3D from here? No, but it would be about the same as using OpenGL, which I already do, so. Except it would be easier to debug, probably. Do I regularly exercise my programming skills and design skills daily? Do I feel rusty when stepping away for a while? Well, I've been programming daily for a long time now. I hadn't, yeah, so for the past year, I spent a lot of time not designing, and I felt a little bit rusty, but then I sat down and started doing levels for this new puzzle game, and they went pretty fast, and I was happy with it. So I think it comes back to you real fast. Do relative pointers mean you can do more with type info pointers, like deserialize arbitrary data structures consistently without needing to know types? I'm not sure I understand the question. I'm not picturing, like, you need to know what type something is to understand the data layout. So I'm not sure what you're getting at. If you could maybe rephrase the question or expound upon it in some way. So there's no C++ interface right now. There probably will be eventually. So right now we only call C procedures. So if we were to interface with DirectX, then yeah, we would use the C bindings. But that's what a lot of languages do. So I don't think that's atypical. But we do, for the purposes of interfacing with other people's game engine code, we're going to want to do like, understanding C++ name mangling and being able to call out to stuff or whatever. Do we use SDL? No. No, we use our own things. Part of the goal of writing this game engine is to give people the equivalent of something like SDL in our standard library on day one, so they don't have to like search around to find something usable. I won't prevent people from providing alternatives to what's in the standard library if they want to do something that they think is better. But we want to, out of the box, give you good code for drawing and playing sounds and stuff like that, so that you don't have to go on the internet and search for things. So if I were to use something like SDL, that would be counterproductive toward that goal. So that's why I'm doing it from scratch. Link to video of engine, or was that stream only? If so, no biggie. If someone wants to paste a link in the chat, that's fine. I was just referring to the Reboot Develop talk that I gave about a month ago in Croatia. It is not on my YouTube channel because YouTube doesn't let you link other people's videos on your channel. There we go, it's in the chat. I'll also put it in the YouTube text for this video. You are welcome, Dan Zaidan. Is it possible to bootstrap the compiler and use this as a scripting language? It will be. Right now we don't really export an interface to the compiler like as a library, but that's a design goal of like the final product, right? You're going to be able to just call out to the compiler and compile stuff. So yes, you would be able to use this as a scripting language or whatever. Do I think new programmers and game designers benefit from starting from scratch more than starting at a higher level? It depends on the individual person and their personality and where they are. I think from the very, very beginning, if you're just trying to learn at all, then I don't think you necessarily want to start from scratch because you don't have any context. And there's a lot of power to being able to make things happen quickly that it feels powerful and it feels neat. And also you just get a scope for like what can the computer do and how can it do it. So you maybe want to use a higher level language when you're starting, right? I used BASIC when I started. And then that idea extends to like maybe using libraries or a game engine or something, right? If it's somebody's first attempt to make a game do something, go ahead and use the Unreal Engine with blueprints or whatever. Like, it's fine, right? I think it's just, as you're building skill as a programmer, you want to then understand how everything happens. Otherwise, you're limiting your own knowledge, which is not a good idea. So it's as you advance that I think it's important. You don't have to rebuild everything for yourself, but you should be able to rebuild everything, given an infinite amount of time or whatever. How large in megabytes is the compiler? Well, the compiler has no data, and the executable is right here. It's a 14 meg executable. I don't know why that is so big, honestly. I guess Visual Studio makes big binaries these days. I guess. Oh, and then also there's the modules folder. There's going to be some junk files in the modules folder. This is an upper bound. So that's 5 point something megabytes. So it's 20 megabytes is like the upper bound of how big the compiler is right now. Yeah. Will the compiler standard lib be baked in the executable so you can copy one file around as the compiler? Well, maybe. That's an interesting idea. The problem is, well, you're going to want to update your standard library, the equivalent of your includes. And also you want multiple versions. Like when I distribute a program, I'm going to want to say, this is like uses version 1.2 of the print function, and that's been modified since then, right? Or whatnot. That's actually maybe that's the fourth major feature that needs to happen. There's so many things. That won't happen until after, like I'll do a test release of the compiler to a limited circle of people, and that won't be in there yet. But you know, you're going to want to. So I think the idea that there's two ideas about the way that you provide compatibility, and I think one of them is poisonous and stifling. The one that's poisonous and stifling is, here's our standard library headers, and we're just going to keep updating these as time goes on, and our updates are going to be constrained to provide the same API to you forever or whatever, right? I think that's fine for bug fixes, but sometimes you need to fix real problems. Like sometimes the API is bad and you need to make it better or something. And I think then you just break it and you make a new revision and you let people compile to the old library, or you let them compile to the new one, right? And so we're going to do like that. And so you're going to want to be able to update is all I'm saying. So it won't be that baked into the executable. What did I know about compiler creation before starting this project? When I was in college, one of the reasons I dropped out of college was because I liked making programming languages more than doing the actual classes. So relative to most people, I had quite a bit of experience in toy languages. But I took some far enough that, I wrote programs in them that worked, but I never took anything nearly this far, right? And most of them were interpreters and not compilers as well. This one, by the time I gave the first demo in, October 2014 or whenever that was, over 2 years ago, I already had that little Galaga game that was a whole game rendering in OpenGL, which by itself was probably further than I'd taken any of my other toy projects. Someone's asking, why do I use Windows 10? Because Linux is more painful. Is there any language feature that would help with optimizing binary size? I think having a good picture of what is taking up size in your binary helps. And we've shown features related to that before. So like the Go Bananas demo showed, the sizes of various functions and stuff. So I think if you have that kind of facility and you could tell what's taking up space code-wise easily, then that's good. How is progress going with regard to thinking about a binary module format? I already answered that question 10 minutes ago. How much work went into compressing the witness? It was not trivial. It was not trivial. Although, at the same time, we also didn't work forever on it. Like, we're actually compressing the data more now that we have to release on mobile platforms that'll kill us if we use more than 500 megabytes of RAM. So with any optimization thing like that, you can put an infinite amount of work in So we're just putting more in now. Have I ever had problems with my arms or wrists? A little bit, like by typing, but usually that's due to problems in, the relative level of the keyboard or the angle at which I type. So I use a laptop a lot, and I'm very picky about laptops. I don't buy laptops with off-center trackpads and keyboards. Like laptops with number pads on the side are a bad idea because you kind of are scrunched over to the side. It doesn't seem like much, but I think that leads to problems. Of course, basically all laptop keyboards these days are garbage, and that's bad for your hands too, so whatever. Do I think compute shaders would benefit image editors, or just doing normal software rendering would be sufficient? Well, I think first you have to get your image editor working, and that should just use software. And then, once it's totally working and doing what you want, then if you want to make it faster, you could try using compute shaders. And then hopefully, architecturally, you thought about this plan and you made it not totally ridiculous to try to introduce compute shaders into the architecture. Any plans for a package manager like Cargo for Rust? I don't know. I mean, I want it to be very easy to get new stuff, but at the same time, I really like. I've never used Cargo or anything like that, but the fact that so many hacker news people think it's great makes me presume it's terrible. That's my own personal bias, but I mean, all these people use Git and think Git is amazing, and I'm just like, I don't know what you people are smoking, right? So, yeah, I don't know, man. So I don't know much about how those package managers work. I would like it to be easy to pull stuff down, but I don't want a rat hole around the package manager, right? So I've used CPAN with Perl sometimes, and that's a little bit good, but not as good as it should be. I should be able to say, pull down all the dependencies that this program wants. And that should just happen, and I shouldn't have to think about it. But yeah, I haven't thought about it more than that. Why is it so bright in SF? This is not San Francisco, this is Seattle. How many lines of code is the compiler? 37,491 when you strip out comments and new lines, which is like 0.3% the size of GCC or something. I don't know. Yeah, pull all dependencies, I think, is important. And then we'll see. We'll see if we need, once you have that, you also have just pull down a package called this, or query for who implements this function, right? And once you've got those couple of things, I kind of feel like that's most of what you need. Maybe I'm wrong, but like I said, I haven't used Cargo or any of these web people's things, so I don't know what they do. Did I say there was another feature I'm going to demo soon? The next demo is going to be probably Friday, and it's going to be just a collection of smaller things that have been implemented. Like, I consider relative pointers a big feature because it like touches the core of the language, or